All right, lesson 8, inverse functions. Our skills and learning objectives, we're going to verify two functions or inverses algebraically and graphically. We're going to use the horizontal line test to determine if functions are one-to-one. We're going to find inverse functions informally and algebraically. We're going to use function notation to describe real-world scenarios. And we're going to analyze and choose the appropriate method to find the inverse of a relation or function. So in 8a, first talks about one-to-one functions. And it reminds us before that, though, it says, remember that a relation is a set of ordered pairs. No rules, any set of ordered pairs is a relation. Then we have a function that is a relation in which for each distinct x value, there's exactly one corresponding y value. That just means that none of your x's are repeated, remember, for it to be a function. And then it says if a function f is a set of ordered pairs x, y, then the inverse of f is going to be the set of ordered pairs y, comma, x. And so remember, for the inverse function, you just switch the x and y's. And when the inverse of a function f is itself a function, then f is said to be a one-to-one function. A one-to-one function says no x's and no y's are repeated. All right, so one-to-one functions here. It says a function f is a one-to-one function if for elements a and b in the domain of f, a cannot equal b implies that f of a does not equal f of b. That is, different values of the domain correspond to different values of the range, which is what I just said, that no x's or y's are repeated. X's and y's do not repeat. So remember, x can't repeat to be a function. X and y can't repeat to be a one-to-one function. All right, example 1 says justify each mapping with an observation. So you can see the first one here. You got your domain, you got your range, and it says it's a one-to-one function. And that's because no x's or y's are repeated. If either one of those was repeated, then it would not be a one-to-one function. And so we can see here on the second one, it tells us that it's not a one-to-one function because right there the y value is repeated. It's still a function because none of the x's over here are repeated, but it's not a one-to-one function because the y value is repeated. And then we can see on the last one here that x equals 1 is repeated, therefore it's not a function. If the x is repeated, it's not a function. All right, if the graph of a function f is known, you can use the horizontal line test to determine whether f is a one-to-one function. So we talked about before the vertical line test, and remember we used that to see if a graph was a function. And that's why we took that vertical line or your pencil and we went across the graph, and as long as it didn't touch it in more than one spot, it was good. Or the horizontal line test says if every horizontal line intersects a graph of f in at most one point, then f is said to be one-to-one. So like if I look at this graph right here, just this black line, I'm going to take my horizontal line here and I go down it, and it only touches it one time in each place, therefore that is a one-to-one function. So before we talked about the vertical line test, which was straight up and down, and it only touches it once, so that makes it a function. But the horizontal line test tells us if it's a one-to-one function. It tells us if the inverse will be a function. All right, so properties of inverse functions. Graphs of inverse functions are reflections in the line y equals x. So if you graph a function and you graph its inverse and you graph the line y equals x, you'll see that the two functions are reflections across that line y equals x. Given a function f of x, the notation for the inverse function is, it looks like f raised to the -1 of x, but that's read the inverse of f of x. And because with inverses, remember your x and your y's are going to switch, that means so is your domain and your range. And so the domain of the function is equal to the range of the inverse, and the range of the function is equal to the domain of the inverse function. Example 2 says for each of the graphs below, draw on the line y equals x. Then we're going to sketch the inverse of the function on the same grid, and we're going to tell is the function one-to-one. All right, so the line y equals x is the line that goes through 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. And the same thing negative. So negative 1, negative 1, negative 2, negative 2, negative 3, negative 3, negative 4, negative 4, negative 5, negative 5. All right, so there's my line y equals x. And then I'm going to sketch the inverse of that function there on the same grid. Well, if nothing else, I can take and I can pull some ordered pairs off of the one that they graphed already. So I see I have, what's that, negative 3, negative 2. Just looking at the whole numbers, I have 1, 0. What's that, 6, 1. And so for the inverse, remember the big thing of the inverse is x and y switch. And so for the inverse, I'm literally just going to take those ordered pairs and switch their x and y. So 2, negative 3, 0, 1, and 1, 6. I'm going to graph those points. I'm sorry, that was negative 3, negative 2. That's why it's not making sense here as that point, which would make that negative 2, negative 3 here. Okay, now it's making sense. Because what I should be able to do, because remember there's supposed to be reflections, is these 2 points should be a reflection. And when I was looking at graphing the other one, I was looking at it over here, and I'm like, there's no way that's a reflection of that other dot, so I knew I was wrong somewhere. All right, so negative 2, negative 3, 0, 1. And so that one should be a reflection of that point right there, and it does look like it. And then 1, 6. And that one should be a reflection of that point. It does look like that line y equals x splits it, comes down in between them. Then we're just going to connect our points and look at our graph. Do they look like reflections of each other? They do. Is it 1 to 1? Well, we could have checked that before we actually even drew in the inverse function, because I can look at the horizontal line test and I can see that it's only going to cross that graph of that line one time, so therefore it is 1 to 1 function. All right, what about B? Well, let's go ahead and answer that question first. Is B a 1 to 1 function? All right, it touches it twice there, doesn't it? So this one is not 1 to 1. And then let's graph its inverse. So I'm going to go ahead and draw in the line y equals x. And I'm going to pick some points on this graph. So I see what, negative 3, negative 7, negative 2, 2. I'm sorry, it's positive 7. Up there, negative 3, positive 7, negative 2, 2, negative 1, negative 1, 0, 2, 1, negative 1, 2, negative 2, and 3, positive 7. So when I go to do the inverse of this one, I just have to switch those x and y's. So 7, negative 3, 2, negative 2, negative 1, negative 1, 2, 0, negative 1, 1, negative 2, 2, and 7, 3. And I'm just going to graph those. My sign's off. No? My sign is off here. Oh, sorry guys, I'm really messing these signs up here. Just be careful, it means you got to watch me. So when I look at this, I can see that there are reflections across the line y equals x. I can look at this part here. The vertices there, I can look at it. Right here with right here does seem to be a reflection across that line y equals x. Also, you can see that that inverse, what I just drew there in red, is not a function. That's why the original one is not a one-to-one function. All right, so definition of the inverse of a function says let f and g be two functions such that f of g of x will equal x for every x in the domain of g, and g of f of x will equal x for every x in the domain of f. So when we take their compositions, when we plug them into each other, they're both going to have to equal x if they are inverses. The function g is the inverse of the function f, and is denoted as f and the inverse of x, or the inverse of f of x. Therefore, f of the inverse of f of x will equal x, and the inverse of f of x will also equal x. The domain of f is equal to the range of the inverse and vice versa. All right, well, that was a mouthful. So all they're saying is that if we take their composition, whether we call the second function g of x, or we say since it will be, we think it is the inverse of f, we could put the inverse of f of x. It's just notation. All right, so whether we write it as f of g of x like that, which would be the same thing as f of the inverse of f of x, as long as g of x is the inverse of f. All right, so example 3 said to show that each function is the inverse of the other. So when it says show, that's not saying find the inverse of f of x and see if you get to g of x. It wants you to do that composition, okay? It wants you to take g of x and plug it into f and see if it equals x. It wants you to take f of x, plug it into g, and see if that equals x. Okay, so when it says show that they're inverses, it's not saying take one of the equations and compute its inverse. Those are two different things. So let's do this. So we're going to take f of g of x. So f is my skeleton, because it's on the outside. And I'm going to plug in g. And you need to show a little work here. Show me how you're getting it. So my 4's will cancel. Then my 3's will cancel, and we get x, which is what we wanted. If this one was not equal to x, we would say they are not inverses, okay? Then we're going to do the composition the other way. So we're looking for g of f of x. So now g is my skeleton. And we're going to plug in f. Okay, so we end up with 4x over 4, which gives us x. And so because f of g of x is equal to the same thing as g of f of x, and they have to equal x, we can say that they are inverses. It's not that they're equal to each other, it's they have to equal x, both of them, okay, to make them, to show that they are inverses. All right, to find the equation of the inverse of y equals f of x, given a formula for the function f, find an inverse by. We're going to determine that the inverse exists. That is, we're going to check to see if the function is 1-to-1, or is it necessary to restrict the domain to make it 1-to-1. Then we're going to interchange the x and y in the formula. We're going to solve for y to get the formula for the inverse of, or the inverse of f of x. We're going to state any restrictions in the domain, and then replace y with that inverse of f of x notation in the new equation. So example 4 here. You might want to write a little smaller. It's got some work for us to do, okay? It says for each of the following functions, we're going to sketch the function and y equals x. We're going to state the domain and the range. Then we're going to find the inverse and state its domain and range. We're going to sketch the inverse. We're going to verify that their inverse is algebraically. All right, so let's sketch this inverse. Now, I'm going to think back a little bit here. We got the square root of x as our parent function. And so I'm just going to write this up here. So the square root of x, remember we took numbers that we could take the square root of to get a parent table back when we did that. And this says that we're going to take x. All right, so this is for f of x. So our x's, we're going to, it says plus 3. So with x, we know we do the opposite. So we're going to subtract 3. And our y's, we do what it says minus 2. All right, so subtract 3. Subtract 2. And let's graph that. And I can't actually graph the last one. We know it's going like that. And so we can tell that our domain is going to be, was it -3 to infinity? And our range is -2 to infinity. All right, so we did A. Let's put A right there. B says find the inverse and state the domain and range. All right, so this is what's new right now to us. So we're going to find the inverse. So I'm going to do that right in here. So the first thing is I know f of x is the same thing as y. So my equation is y equals the square root of x plus 3 minus 2. And then it tells us up above here, step 1 is to interchange x and y in the formula and then solve for y. So every x becomes a y, every y will become an x. And we're going to solve for y. So I'm going to move the 2 over. And then I got to get rid of that square root. So I'm going to square both sides. So I get x plus 2, all of it squared, equals the y plus 3. And then subtract the 3. So we get x plus 2 squared minus 3 equals y. And then the last thing we do is we change it back to function notation. So instead of putting y equals, we're going to put the inverse of f of x equals x plus 2 squared minus 3. Now remember now, x plus 2 squared is quadratic. Okay, so we've got a quadratic function, which I know when I graph it, it's going to look like this. That's not a one-to-one function, so we're going to restrict it. So to help us figure that out, first thing I'm going to do is I'm going to use what we already graphed to help us. So for my inverse, remember f of x, x and y are just switched. And so I didn't actually graph that one, so I'm not going to use it. So I know it's going to be -2, -3, -1, -2, and 0, 1. All right, and we can picture it if we drew in the line y equals x. We could see that they are reflections across that line. I didn't draw that in, and it actually had said to in A. I missed that part. So we can see there are reflections across that line. Now, notice what x values are we using. We're using -2, -1, 0, and our arrow keeps going to the right. So we're using x's that are greater than or equal to that -2. So when we write out our equation, we put x is greater than or equal to -2. So there is our inverse. And then it says state the domain and the range. Well, our domain is going to be that -2 to infinity. And our range is -3 to infinity. And we already knew that because remember, It's the opposite of the domain and the range of the original because x and y switch. And then, let's see, sketch the inverse. We did that. Verify that they're inverses algebraically. All right, so let's see. We just did C over here as well. And so D, I'm going to put in this little blank area right here. Find that the inverse is algebraically. So we're going to take f of the inverse of f of x. So that means the original one, f is my skeleton. So square root of x plus 3 minus 2. And we're going to plug in what we got down there. So that x plus 2 squared minus 3. Okay, my 3's will cancel. So the square root of the x plus 2 squared minus 2 at the end. The square and the square root cancel. We get x plus 2, and then that minus 2, the 2's cancel, and we get x, which is what we wanted. Remember, if there's anything other than x, that these would not be inverses, which means we made a mistake. And then we're going to do the opposite. We're going to take the inverse of f of x. So now my inverse is my skeleton. So it's x plus 2 squared minus 3, and we're going to plug in f, which is the square root of x plus 3 minus 2. And inside here my 2's will cancel, and so I end up with the square root of x plus 3 squared minus 3. The square and square root cancel, so we get x plus 3 minus 3. The 3's cancel, and we get x. Is what we wanted, so we show that they are inverses algebraically. All right, example 4. Continued here. So we're going to do the same thing, just a different function. All right, so we're going to sketch the function, and y equals x, state the domain and range. So again, I'm going to come up here. This is a cube root function, so I'm going to have to think back. So the cube root of x, it also had a different table. I want numbers I can take the cube root of, so like negative 8, negative 1, 0, 1, and 8. I take their cube roots. And then this one says x plus 2, so we know we're going to subtract 2 from our x's, and we're going to subtract 1 from our y's. All right, so I can graph that. Can't actually graph that one, so I'm going to mark it out. So negative 3, negative 2, negative 2, negative 1, negative 1, 0, 6, 1. That one's not really on there, but I'm going to use it because I don't want us to think that's linear. If I try to connect these, I'm tempted to just do like that, right? But you got to remember that cube root is the one that looks like a cubic, but it's off to the side. So we got this little swirly thing going on here. All right. I'm going to go ahead while I'm thinking about it, graph that line y equals x. I always do it as a dashed line. I didn't talk about this earlier, but I do it as a dashed line because it's really not a part of our graph. It's just there to help us check our graph. So it's kind of like that asymptote. It's not really part of our graph. It's there to shape it. This is just here to help us check our graph. So that's why I do it as a dashed line. All right. Then I can see that my domain is going to be negative infinity to infinity. And our range is also negative infinity to infinity. All right, so there's A. B wants us to find the inverse of the function. So we know that this is, so for B, let me move this over a little bit. So this is y equals the cube root of x plus 2 minus 1. So we're going to switch our x and y. So every x becomes a y, every y becomes an x. And then we're just going to solve for y. So I'm going to add the 1. I've got to get rid of that cube root, so I'm going to cube it. So I get x plus 1 cubed equals the y plus 2. And then just subtract the 2. So we get x plus 1 cubed minus 2 equals y. Once you get y by itself, then change it back to function notation. So this was g of x, so this is going to be the inverse of g of x will equal x plus 1 cubed minus 2. Now, without even graphing it, you should already know your domain and your range, because your domain is the range of your inverse, the range of your original function, and the range is the domain of your original function. So we should already know them, and we're going to check that when we graph it. All right, so when I go to graph the inverse, I put g of x up here. F of x, it should have been g of x. I apologize. I'm just going to switch my x and y's. There we go. We know it's a cubic function. It should have that little swirly shape going on there. I can look at my domain and range. It is negative infinity to infinity for both. All right, we also did C because we sketched it. And D says to verify that they're inverses algebraically. So again, we're going to do some plugging in. So we're going to take g of the inverse of g of x. I have a little more room here. So g is the cube root of x plus 2 minus 1. And we're going to plug in g of x, which is x plus 1 squared minus 2. Work underneath that radical, so those 2's will cancel. And we're left the square root of x plus 1 squared, and then the minus 1. The square and the square root cancel, so we just have that x plus 1 and then the minus 1, which gives us x. And then do the inverse of g of x. So now inverse is my skeleton. So it's x plus 1 cubed minus 2, and we're going to plug g, the original one, into it. So that's the cube root of x plus 2 minus 1. We can work in the parentheses, our 1's will cancel. So we get that cube root of x plus 2 cubed minus 2. The cube and the cube root will cancel, so we get x plus 2, and then the minus 2. 2's cancel, and we get x. And so we proved algebraically that they are inverses of each other.